Okay, so welcome back to Stats. The plan for today is to finish up one last slide in the Chapter 1 PowerPoint and then start into Chapter 2 talking about graphical techniques for describing data. The Chapter 2 homework is posted on my Stat Lab, and note that starting with the Chapter 2 homework, you have 5 attempts per problem. So the Chapter 1 homework in the first assignment, you had unlimited attempts. That was just kind of getting a feel for how my Stat Lab works and so on. But now that we're into kind of some of the more major material for the course, from this point on, you'll have 5 attempts per problem. So still, I think a pretty generous number of attempts, but you will want to be a little bit more careful about how you approach kind of studying and doing the homework and so on, and be a little more careful with the attempts on the homeworks. The quote of the day today is, I suppose it's like a paraphrase of something that Ralph Waldo Emerson wrote. With a lot of these quotes that kind of somebody famous like writes in a letter or maybe even in a book, over the years, people come up with maybe more succinct ways to say it or more catchy ways to say it. But the quote of the day is, "What you do speaks so loudly that I cannot hear what you say." So in other words, actions speak louder than words. Uh, but to a very great extent. It's not just that actions speak a little bit louder than words, but a lot louder. And I think what this kind of makes me think of is this question, if you ask most people, like, write me a paragraph saying what you value most in life, people would write a paragraph, and a lot of people would say maybe things about like family and health and security and these different things that people tend to value, friendships. And then if you ask them a different question, if you say, where do you spend the majority of your resources? In other words, your time, talent, and treasure. If you looked at your bank account over a month or a year, or your credit card statements, or if carefully wrote down what you did each day for a month, how much time you spent on this versus that thing, uh, what does that look like? And I think we would agree that in theory, there should be some concordance there, right? We would expect that we spend more time and resources and so on things that we value more. But I think a lot of us, and I mean myself in particular, we often fall into the trap of like, oh, I spent, 3 hours today on TikTok or something, or 2 hours arguing with some random stranger on Facebook about some meaningless thing, right? Like, so I think it's good to check in on that every once in a while. Are the things that I'm doing, are my actions uh, saying the same thing that my words are saying, in terms of important things like my life goals and so on. And this is, I think you need to get this right before you worry about whether somebody else looking at you thinks that your actions are concordant with your words. So that's the quote of the day, the idea of the day for today. Okay, so let's jump over to the Chapter 1 PowerPoint, and we had gotten to this point last time. I don't know why the aspect ratio is so wonky. Oh, okay, this is because I said I'm still getting used to my kind of 2 displays set up here. So it's because I moved it from one display to another and it didn't readjust that. All right. So we had gotten through all of the Chapter 1 PowerPoint except this last slide on bias. So that's what we're going to talk about today. Sorry, my allergies are still bugging me. They've been bugging me all week. So I did also post, let me turn this off. In the supplemental material folder on Blackboard, I posted the Chapter 2 PowerPoint, as well as a couple of additional things we're going to talk about in a minute here. One of them we've already talked about. Oh, I actually already had those open. That if we look at the S&P 500 kind of historical chart, we look at it, we say, oh, okay, I see the .com bubble and crash. I see the housing market bubble and crash. I see the, tear that the market's been on in the last several years. But I look back at, say, where I think the Great Depression might be, somewhere in this ballpark on the left over here. And it doesn't look so bad, right? Why is the Great Depression this huge historical event? Remember, we talked about inconsistent units and the fact that on the right-hand side, we're dealing with something like $2020, where on the left-hand side, we're dealing with something like $1920. A dollar meant a very different thing 100 years ago. But one way to approach this was to look at, say, annual rates of return on the market, with positive or negative. Another way to approach it is to use a log scale. And we're going to talk a little more about log scales in chapter 2. So this is kind of introducing some of the ideas that we'll see in chapter 2 as well. But if we change the scale of the graph, note that over here we go like 500, 1,000, 1,500, 2,000. So one tick mark on the y-axis represents 500 units, more or less $500. Where here, one tick mark represents multiplication by a factor of 10. Or yeah, 10 to 100 to 1,000 to 10,000. So I'm multiplying instead of adding as I go up the y-axis. That's what we call a logarithmic scale. And you see that we have generally this kind of nice, smooth upward trend. We do have our dot-com bubble and crash. It looks, not like a great time to be in the market there. Or the housing market bubble and crash. Again, maybe not a great time to be holding assets during that slide. But now all of a sudden we look back at the Great Depression, we see, okay, yeah, that's a lot different, right? This logarithmic scale helps to mitigate some of the effects of that difference in the dollar value over time. So that would be another way of approaching a problem that we talked about last time. Okay. So moving on to our discussion of bias. I'm going to try to not use my mouse because it's probably clicking like right in your ear. But it is a lot easier for me to move things from window to window using the mouse. So, okay, so discussing the idea of bias. Remember that in statistics, I mean, there's all kinds of definitions of the word bias in different contexts, but in statistics, when we say bias, what we really mean is we have our population here. We typically don't have the resources or the ability to study the whole population, so we take some individuals from the population and get a sample. And maybe I'm interested in, say, the population average. This is what I would like to know, but I don't have access to. They say the average height of people in Pittsburgh. But I can compute a sample average, but that's not exactly the thing that I want. And I kind of hope, or maybe I'll, attempt to prove mathematically that under some constraints, when I compute a sample average, it's a good estimate of the population average, that knowing what the sample average is gives me a lot of information about what the population average is. However, I might not have constructed my sample in a way that makes this true, right? We talked about the example, kind of silly examples, but what if I was interested in average heights of people in Pittsburgh and I went to a kindergarten and took my sample there, or if I went to, a basketball practice and took my sample there, that's probably not going to be a representative sample. So that's the first type of bias we can have, is selection bias. This would be like taking my sample from a basketball practice or from a kindergarten, right? The ideal is I take every person in the population, assign them a consecutive number, 1, 2, 3, 4, 5, and so on, and then I randomly choose numbers, and those are the people who I sample. We're never going to get perfectly to that ideal in practice, but we would hope to be close to it. If I go to a kindergarten and take my sample there, that's surely not doing something like that. So how I've selected my sample is it was done in a way that's fundamentally not representative of the population. Another issue that with selection bias these days is machine learning, artificial intelligence, all of these kind of things. There are hot topics, right? But if we think really quickly, just how do we make a machine learning algorithm? How do we make a chatbot or something? Well, we take a whole bunch of input. Some of the first machine learning programs were just to read numbers that were handwritten, to say, okay, there's somebody wrote a number and that one looks like a 9 and this one looks like a 3, something that humans can do really well. This was developed for the post office so that the post office machines could read zip codes and route the mail a lot more quickly. So, and that data set is still out there. So what is selection bias? Well, I have to choose a ton of handwritten numbers to feed to the machine, and it makes a guess. I give it the answer. I say right or wrong. It adapts. I feed it another number, another handwritten number. It makes a guess. And hopefully over time, when it gets this feedback for these guesses and that feedback leads to certain adaptations in the model, hopefully over time it gets better and better at recognizing handwritten numbers for what they are. But if I were to select handwritten numbers all from somebody who had perfect handwriting, and then we try to apply that to the real world with people who write more messy, that model's probably not going to work very well in general. It's not going to generalize to the population. Or if I used one person and had them write numbers, 10,000 numbers, they're probably going to have the same little idiosyncrasies, and the algorithm's going to pick up on those idiosyncrasies, and maybe it's calling a 9 not because it looks like a 9, but because it has this little curve on the tail or something that this person always puts there, and it's not going to be able to generalize to the population. And that's a bigger issue when you look at things like, say, chatbots. Maybe they're trained on historical literature. A lot of that literature is, from certain demographics, or at least certain demographics are more represented in it than
Do
other.
you guys have any extra guest badges?
Sorry, I don't think I. All right. So anyway, that idea of selection bias is a super important idea in machine learning these days. Very hot topic. And I'm not sure if there's a good solution to it yet. So selection bias, probably the easiest to understand source of bias. And again, this is where we choose a sample, and for whatever reason, that sample was selected in a way that's not representative of the population. The next one, confirmation bias. And maybe in everyday life, this might be the most important bias. Certainly it applies to statistics, but it also applies to how we make decisions every day, and really even how we filter out information, right? Every day as we're going around the world, we get tons and tons of information input, and we have to throw most of it away because otherwise it will be too much for us to handle, to process. So what do? We take information that kind of meshes with our mental model of the world, and we incorporate that. We accept that information that doesn't mesh with our mental model, we kind of throw out. That works pretty well most of the time. But if we're, say, scientists evaluating the likelihood of this or that hypothesis being correct, well, we might have a desire for this hypothesis to be correct. Maybe this is the hypothesis we came up with and we think is really interesting, or if it's correct, it will further our career. We might have a tendency to to look at the data, and the data that supports our hypothesis that we want to be true. Maybe we overweight that data and in our minds, and we underweight the data that would stand against our hypothesis. So that's the idea of confirmation bias. And the scientific method, this kind of whole mental model of I'm trying really hard to disprove myself, to disprove my model, to work against my biases. It attempts to eliminate some of this confirmation bias. And then whenever I take my model, and if I think I've proven it, put it up for peer review so that everybody else can look at it and try to tear it apart. That goes a little further in trying to avoid this problem of confirmation bias.
Sorry, could you say what confirmation bias is again? A little bit simplified.
Is there a question? I didn't catch that. There was a lot of background.
Sorry, could you hear me?
Yeah, I can hear you. There's a bit of
Could
background.
you repeat what confirmation bias is and just like a little bit more simplified, please?
Oh yeah. So the idea of confirmation bias is if we have data that's presented to us, we're more likely to accept data that confirms what we think is true than data that refutes what we think is true. So if I have a mental model about how I think the world works, maybe a pharmaceutical researcher, I've come up with a new chemical that I think will help treat this problem, this disease better than the existing chemicals. If it's my chemical and I stand to make career advancements or money based on its success, not even necessarily malevolently, but I might just inherently be more likely to overweight evidence that comes in that seems to support my chemical, my drug being effective, and underweight evidence that comes in that suggests that my drug isn't effective. So that's the idea of confirmation bias. If I go up to data, if I start to look at data with a particular worldview, with a particular mindset, I'm going to be more likely to accept data or to give higher weight to data that confirms what I already think that I know than data that refutes what I think that I know. So the next one, kind of an interesting one, survivor bias. And I have a cool little example for this one. Let me bring the picture over here. So this is also in that supplemental material folder on Blackboard. Um, so the story behind this picture, this is a kind of a mock-up of the original picture. This guy, Abraham Wald, statistician, he was working in, I think, England at the time, but he was doing work for the Royal Air Force in World War II. And so the Air Force has planes, they go up, they get in, whatever dogfights with other planes. They come back and, some of the planes get shot down, some of them come back. And the Air Force was trying to figure out, okay, we would like to put more armor on our planes so that they're more robust, so they're less likely to get shot down, they can survive longer. But obviously, these are airplanes. If we can't just make them into tanks, right? If we put armor all over the place, really thick armor, they can't even take off, or even if they could take off, maybe they're less maneuverable. So we want to put a bit more armor on the planes, but only where it's extremely high yield, only where that armor is going to really serve an important function. We don't want to put armor just everywhere on the plane. So they brought in Abraham Wald and asked him, okay, where should we put the armor, right? How do you decide where to put the armor? So what he did is he sat on the side of the airfield, watched the planes take off, the Royal Air Force planes. They'd go out, get into dogfights. He'd watch them come back and land. And when they came back, he would note on a little piece of paper where he saw bullet holes in the planes that came back and landed. And based on a picture that, say, looks something like this, he makes a recommendation to the Royal Air Force. Where do you think he recommended that they put the armor? It's a little bit of a trick question. So if this was his data set where each of these red points is a place that he saw a bullet hole in the plane when it came back, where would he recommend they put the armor?
On the red spots, like those
Yeah,
areas.
so this is why it's a bit of a trick question, right? We would think the red spots, right? That's kind of the natural answer. But the thing is, he recognized that there's a survivor bias here. In other words, these were planes that came back. So a plane that got hit in the middle of the fuselage or at the tips of the wings, they actually were able to survive that hit. So if we put armor there, that's not really helping the plane all that much. It was able to come back and land with a hit in those areas. But a plane that was hit, say, in an engine, we don't see any red spots there. So presumably the planes that were hit in engines are the ones that crashed. They were the ones that didn't survive. Or the plane that was hit kind of in the middle of the wing where maybe the fuel tanks are. or say in the cockpit where the pilots are, those are the planes that presumably crashed and did not survive. So those are the areas that we actually want to put the armor. So this is survivor bias. The data that he recognized was from the survivors, from the planes that made it back. So presumably, you would expect that if planes are just shooting at each other, you'd have a pretty random distribution over the whole plane of places it was hit. And presumably the ones that were hit in these places that we don't see bullet holes from the planes that came back and landed, presumably those ones crashed. Yeah, so that was Wald's conclusion. Another example of survivor bias. I think a lot of folks in this section are going into things related to either like finance, things like that, finance, accounting. I think actually a lot of folks are going into computers as well, if I remember right. But an example from finance is hedge funds. So if you look at, all the hedge funds that are out there today, and people do this, they've gone through and they've studied them and they've said, what's their average annual rate of return over the past 10 or 20 years? And it turns out that it's really good. It's like, way better than you can get investing yourself or investing in a mutual fund. But one of the issues is that hedge funds, they're kind of like mutual funds, but they're much less regulated. They do really, really risky things, and they occasionally go bankrupt. Mutual funds basically never go bankrupt. So if I'm looking at the hedge funds that are existent today and looking back and seeing what their performance was, well, of course, they're the survivors, they're the success stories. Their rate of return is going to be pretty high. But if I were to say rewind 20 years and look prospectively, say if it was 20 years ago, look at the cross section of all hedge funds and look forward at how they did, and I incorporate the fact that I might choose a hedge fund that goes bankrupt in 5 years or 10 years, then the numbers don't look as good. They still look a little bit better, but it's not nearly as appealing, especially once you take into account the huge fees that they charge and so on. Another example is estimator bias. Estimator bias. So this one's a little harder to explain. So I'll start by explaining it with kind of a silly example, and then kind of point out an important example that we'll actually see come up in chapter 3. So let's say again that I want to compute the average heights of people in Pittsburgh, and what I would like is the population average. But what I have is the sample average. This is what I have. This is what I would like. I hope that when I collect my data, compute a sample average, that sample average is pretty close to the population average. That's my hope. Now, I think we know how to compute an average, most of us. We take all of the numbers we're averaging together, we add them all up, and then we divide by the number of data points that we added together. So if I have a sample of size 10, if I have 10 people's heights, I add up those 10 heights, I divide by the number 10, and that gives me my average height. What if I, for some strange reason, I add them all up and then I, subtract 12? What if this was what I used as my formula for sample average? Again, that's kind of a silly example, but maybe I, when I was typing my formula into Excel or in my calculator, I just hit a couple extra buttons by accident. I made an input error, and this is what my formula says. If I compute the sample average using this formula, it's probably not going to give me a good estimate at all of the population average. Why is that? Well, the estimator, the thing that I'm using to estimate the population parameter, this formula for the sample average, is itself biased. Now, again, you look at this and you say, well, I mean, I know how to compute the population average. I just compute the sample average the same way. Like, who's going to make this mistake? Well, it turns out that in chapter 3, we'll see an example where we have a measure of volatility of kind of how spread out things are. That's our population variance, and it's computed a certain way, and that computation has a big numerator divided by n being the number of data points. We have a sample variance, and it has a numerator that looks very similar. But it turns out if we divide by n in the sample variance, if we use the exact same formula, apply it to the sample instead of the population, it turns out this is a biased estimator. It's a bit complicated to explain why at this point. It's even a bit complicated to explain why after we have gone through chapter 3, but it turns out that we need to subtract 1 on the bottom to make this an unbiased estimator. So there are some situations where the estimator, let's say the obvious estimator that you might want to use, ends up being unbiased, and it's like, okay, that's pretty clear. But there are some situations where the kind of obvious estimator that you think you should use ends up being a biased estimator. You could do great sampling techniques. You could get your data. You could be really careful with collecting and managing your data. And then you apply this estimator that itself is biased, and that introduces bias into the result. So then your sample average or sample statistic doesn't look like the population parameter. So a couple others, those are the main ones that I wanted to talk about, but there's lots of examples of these. One example is detection bias. So sometimes we're studying things that are, in a sense, hard to detect. This might be kind of on purpose or just by chance, right? If you look at crime statistics and you maybe go to the FBI's website and you say, how many people committed assault in the last year or something in some state, you'll get a number. But do you think that that's all of the assaults that were committed in that state? Well, no, there's not a perfect reporting system, right? It's probably the case that if an assault is reported, it actually occurred, or at least if it's, gone through the justice system and the person's been convicted of it, it probably has occurred. At least we would hope that that's true. But that's probably an underrepresentation of, say, all assaults that have occurred. If I go around randomly asking people, hey, have you committed assault in the last year? Again, and after they punch me or something, which maybe is another assault. I don't know. Maybe I'm messing with the statistics myself there. But anyway, if I go around asking people that, it's not the kind of thing that somebody's going to say, oh, yes, that's not the kind of thing they're going to answer honestly. So how do I get accurate information, right? When people are actively trying to hide their behavior. Same thing with something like, say, tax fraud. If we want to say we think that there was this much of a cost to the taxpayers in terms of tax fraud, how do we get that number? You can't just go and ask people like, did you cheat on your taxes and by how much? On one hand, if they knowingly cheated on their taxes, they're probably not going to admit it. And on the other hand, they might have just not done their taxes right. They might have made an honest mistake. How do you detect that if the person made an honest mistake? This comes up in nature too, so it's not always an intentional thing. If you're a biology researcher and you're looking at, is this or that animal, do we think that it's extinct or endangered or whatever? There are some animals that are a lot easier to find than other animals, right? If you have, say, some loud parrot or something in the rainforest, or I don't even know where parrots live. I'm guessing they live in the rainforest. If it's brightly colored and loud and it's like, okay, if there's one around, you're probably going to know it. If you're looking for some like snail or slug or something like that, it's probably going to be a lot harder to detect one if there's, say, one of those within, some distance of you. Kind of an interesting tool they're using these days is, as we go around, as any animal or creature goes around, we kind of lose cells off of our body, our skin cells or whatever kind of slough off. And we actually kind of shed DNA all over the place all the time. It's maybe a little bit gross to think about sometimes, but that's how it is. And so some researchers, or what they're doing is they're going around and just collecting random DNA samples. And at this point, we sequenced the DNA of lots and lots of different kinds of animals. So we kind of know, all right, if I'm looking for this slug, it has like this particular DNA sequence somewhere in its genome that is unlike, basically any other animal or any other animal that's reasonably likely to be in this place. Do I see any of that like uniquely slug DNA or something? So that's a way to maybe combat this kind of bias. But again, some things are harder to detect than others. If you just ask what candidate are you voting for in a phone call, yeah, people are probably going to be more or less honest with that. Another example is reporting bias. Sorry that my handwriting isn't all that great. I spent several years writing on like one screen, and now that I have two screens, my trackpad is a little bit different. It's just taking me some time to get used to using it again. So reporting bias. The idea here is, if I have a finding, am I likely to report it or not? Am I likely to tell everybody about it or keep it a secret? It's maybe a little bit of kind of a detection bias, but there are kind of two canonical examples here. One is in medicine. We'll talk about this a little bit later in the course. But if you open up a medical journal and you see that in some hot area of research, say immunological treatments for cancer, if you look at that research and you see, oh, look at this, I I found that there was this success and that success and that success for this particular line of research, and I don't see any failures, then maybe I'm very convinced. I've, three papers out of three found that this type of treatment was successful. Well, the question is, okay, if you were a researcher and you got a bunch of grant money and you did research in this area and you thought this was going to be successful, but it turns out it just doesn't work, are you likely to publish that? Are you likely to write that up, send it into a fancy journal like Nature or something? They're never going to publish it. They want to, the big journals want to publish things that are groundbreaking, that are new, that are exciting, not the things that are like, I tried this and it didn't work. There's a whole bunch of things that people have tried and didn't work. So there's a bias to report, or at least report in more widely read journals, things that were successful. And if there were three successes and one failure, kind of in reality, if we had all the information, it's probably not that big of a deal. If there were three successes and 30 failures, then we're starting to think maybe those three successes are just kind of flukes, right? The number of failures is quite important, but we don't really usually know the number of failures. So that's a reporting bias. The successes are reported very widely and on front pages of high impact factor journals. The failures, not so much. And in something like finance, we might have an opposite type of situation. In finance, there's this idea called the efficient market hypothesis. And roughly speaking, what it says is that it's impossible to beat the market consistently, like on average, over a long period of time. You might get lucky and beat the market for a year, but you can't do that on average over a long period of time. Well, suppose that I came up with a way that I could beat the market on average over a long period of time. I could publish it. It would be a really interesting piece of academia. But once I publish it, everybody knows my strategy. And then I can't actually use my strategy to make money, because everybody's going to try to use the strategy if the numbers, if the market is situated in a way that that strategy is available, everybody will try to use it. And then that benefit of that strategy goes to zero very quickly. So I could either publish it and not make money, but get some pats on the back, or maybe get a tenured professorship at some university, or get some accolades. Or if I keep it private, I can make a lot of money. It's not clear what a given person is going to choose in that situation. And in fact, we see that a lot of these folks working in finance at fancy institutions like Harvard and so on, they kind of they do consulting work for hedge funds. So it's a little funny that it's like, on one hand, they seem to be saying you can't beat the market on average over a long period of time, and on the other hand, they're getting paid a bunch of money from folks who are charging a lot of money to other people because they claim they can beat the market on average over a long period of time. So it's a little funny, right? And there's more nuance to it than what I'm giving credit for here, but that's a discussion for a finance course, not a stats course. And then just really quickly, status quo bias. We tend to, if there's been a model that has existed and been reasonably successful for a long period of time, we tend to be very hesitant to overturn such a model. So this is maybe a little bit related to something like confirmation bias. But if it's the status quo, if it's the way everybody does it, we're unlikely to overturn that in the face of new evidence than if that model, had just come about and then we got new evidence. And then the last example here, but again, there's many others. The idea of lead time bias. This is more in medicine. And again, I don't think we have too many folks in medicine here, so won't spend a lot of time on this. But kind of in short, an example is, if I say, compared to 10 years ago, people with such and such, let's say this kind of cancer at this stage, live longer, live on average 2 years longer now than they did 10 years ago. Now we might think that, okay, the treatment has gotten so much better over these 10 years that people are living 2 years longer. That could be the case, but we could be adding years kind of to the end of their life that they wouldn't have had 10 years ago. So the same person 10 years ago would have lived till, whatever, 64, and today they live till 66. But we also could be just getting better at detecting the disease. If I can detect that they have cancer 2 years earlier with, say, a blood profile, rather than waiting until they have symptoms from the cancer, even if that doesn't add a second to their actual lifespan, if they still live till 64 now, or 10 years ago, if I discover if I discover the disease 2 years earlier, I have 2 years of lead time. My ability to detect the disease got better, so I just knew about it 2 years earlier, and it appears that they have lived longer with that disease, but I just really found out about it earlier because my detection methods have gotten better. In reality, it's probably a little bit of both, right? If you saw that data, you'd probably think, okay, we probably got, over that 10 years, a little better at detecting it and also a little better at treating it. So we'll probably have a little bit of lead time and a little bit of extra quality adjusted life years we're giving that person. Hopefully quality adjusted life years, because sometimes if we detect things sooner, then that means treatment starts sooner. And even if the treatment isn't effective, maybe the treatment decreases quality of life over that time period. Okay, so any questions on either this slide or anything from chapter 1? All right, let me swap out my PowerPoints here then. I'm gonna try to get this one a little bigger. All right, so again, this chapter 2 PowerPoint is up on the Blackboard site in the supplemental material folder under the PowerPoint slides subfolder. And chapters 2 and 3 really look at descriptive techniques for data. So from this point forward in chapters 2 and 3, we're kind of thinking, okay, I have a data set, I have the raw data. We're hoping that it's, unbiased, that it was collected in a good way, that the experiment was set up with good design and, not introducing these biases into the experiment. So we have the raw data now, but now we want to do something with the data. We want to either maybe crunch it down to say one number, like an average, like we've discussed. That would be something like in chapter 3, where instead of reporting to you 1,000 different heights of people, and you're looking at these 1,000 numbers thinking, how do I make heads or tails of this? If I report one number to you, the average height of the sample of size 1,000 is whatever, 5'7". That's much easier for us to digest, to interpret, to make a decision on the basis of that number. What chapter 2 is looking at is a similar idea of taking all of this data and crunching it down into something that's more digestible, but through the lens of graphical techniques. So maybe making a bar chart or a histogram, maybe making a pie chart, maybe doing something else with the data. So that's the focus of chapter 2. Chapters 2 and 3 are both about taking a bunch of data, crunching it down, making it easier to digest. So easier to understand one facet of it, but at the expense of not having all of the nuance that the original data has. So there is a price to pay for this. But before we jump into chapter 2, to kind of wrap up chapter 1, this is a quote from Sherlock Holmes in one of the books written by Arthur Conan Doyle. Sherlock says Sherlock was a detective. So if you're not, familiar with the series, it was written, I guess, maybe in the late 1800s, and Sherlock was a detective, and has all kinds of interesting exploits and that are recorded in these books. I shouldn't say recorded, that are made up in these books. They're novels. And in one of his books, it says, "It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts." So any thoughts on this? Do you agree with this statement, that Arthur Conan Doyle is kind of saying through the mouth of Sherlock, or do you disagree? Do you think it's conditional? Any thoughts? So I think the big question is, well, if we don't want to theorize before we get data, where does the scientific method come into play here? The scientific method is, kind of roughly speaking, make a hypothesis, come up with an experiment that can disprove your hypothesis empirically, and then run the experiment to get the data. So we need to theorize before we get data. Otherwise, we don't know what data to get, right? If we're trying to come up with a new pharmaceutical drug, are we just going to try a bunch of different random combinations of chemicals and put them in people and see if they cure the disease? Well, no, that would be kind of silly, right? We need to theorize before we have data. Now, when we do that, we risk confirmation bias, which is what he's addressing here. But sometimes we need to do that, right? What's the context here, though? Well, I think it's important that the context is that Sherlock is a detective. And as a detective, almost all of the time, he's showing up on scene well after the crime has been committed. Does he want to do an experiment uh, and try to figure out, if I manipulate this variable or that variable, what happens? Well, no, he's doing a more observational type of study. He's showing up to the crime scene and just looking for anything that seems out of the ordinary. Well, in that sense, in an observational type of study where he's just observing the crime scene, looking for anything that, you know, doesn't seem right, maybe it is a good idea to not theorize first, because I might subject myself to confirmation bias and I might do so needlessly. On the other hand, if we were, experimenters in the scientific fields, we kind of have to theorize before we have data so that we know what data to collect. So I think it's an interesting point, and the resolution is that maybe it's conditional. Maybe in an observational study, we want to be really careful with with our theorizing before we collect the data. But in a scientific type of situation where we're running experimental studies, we're kind of stuck with having to theorize before we have data. And we might want to just appreciate the fact that by doing that, we give ourselves some buy-in, we create more chances for confirmation bias, and we want to just be careful to try to minimize that. Okay, so moving into chapter 2. So we're going to start with the idea of frequency distributions. Our end goal is a graphical technique, a graphical representation, pie chart or something like that. But before we get there, we have to take our raw data that's just kind of all jumbled up. We gathered it randomly, and we have to organize it. So that's where frequency distributions come in. We're going to start by organizing our data into tables. Raw data, as we've mentioned before, data kind of in its original form. If I took a sample of size 1,000 of heights and people in Pittsburgh, this would just be a list of 1,000 heights in no particular order, whatever order I took them in. That's my raw data. A frequency distribution is we take that raw data, we organize it into a table. We use things called classes or bins. We talk about frequencies or number of occurrences of that bin, number of data points that fall into that bin. And we can start by looking at categorical variables. Categorical, qualitative, nominal, those all kind of mean more or less the same thing. So these are, this represents a variable where the results can just be placed into bins. There's not even a natural ordering or ranking. So for example, if we did a survey for a food manufacturer, food manufacturer just doesn't sound quite right, but whatever. And we asked people, which drink do you prefer? Pepsi, ginger ale, Sprite, Dr. Pepper, or root beer. There's not a natural ordering or ranking between these, right? Compared to, say, if we were measuring people's heights, like somebody who has a higher number for their measured height is a taller person. There's a more natural ordering or ranking. Now, we could put these in order if we wanted to. We could like put them in alphabetical order, but that doesn't really have anything to do with the actual drinks themselves or what they taste like or how much people like them, at least presumably, right? Who knows? Maybe people have like a bias for letters that are earlier in the alphabet or something. But at least at first glance, I don't think we would suspect that that's the case. So we ask people, what drink do you prefer? And we might get raw data like this. I see that this is a 5x5 grid, 25 responses. We have a data set of size 25. But at this point, everything is kind of jumbled up. It's a little hard to see what the favorite is, how much of a margin it's the favorite by. I mean, just kind of glancing around, it looks like I see a bunch of A's and maybe, not a ton of D's, but it's a little hard to tell. It's also a little hard to tell because a detection bias kind of issue, some letters just pop out to us a little more than other letters. They're easier for us to recognize. Like you can imagine if there was an F, telling the difference between an E and an F just at a very quick glance is going to be much harder than, say, recognizing a D, which looks pretty distinctive. So what do? Well, we say, what are my classes? What are my bins, my categories? What are the possible responses? A, B, C, D, E. Those are my 5 possible bins. I just list those 5 classes, A, B, C, D, E. And then the frequency is just the number of occurrences. So I go to my raw data, I say how many A's were there. In the first line, I have 1, and then 2, 3, 4, 5, 6, and 7. So there are 7 A's. So I have 7 data points that fall into this bin, class A. I have 4 B's, 5 C's, 3 D's, and 6 E's. It's a good idea after I've completed my frequency distribution to add my numbers together, and hopefully that adds up to the total, and it does. I have the sum of these 5 numbers is 25. I had 25 data points. That's at least a check that I'm, fairly confident that I didn't count an extra one and didn't miss one. I'm probably more likely to miss one than to count an extra one. So I'm pretty confident in this result. And this would be my frequency distribution. Sometimes it's helpful to think of these frequencies as percents instead of actual raw numbers. Maybe I have two surveyors who are doing the same survey, and one goes to, this area, one goes to that area, and we have different amounts of responses. Maybe one surveyor gets 25 responses, and one surveyor gets 150 responses. People are just more cooperative or whatever. There's more people there. It can be hard to, if somebody's on the scale of 25 and another one's on the scale of 150, 6 times as large, it can be hard to compare the frequencies directly to say which one was the favorite and by what margin in both cases. But sometimes going to a percent, then everything is kind of scaled to 0 to 100%, and it can be easier to maybe compare data sets of different sizes. How do I get a percent? Well, I take my frequency over the total. If I multiply top and bottom by 4, I get 28 over 100 or 0.28 or 28%. So I just take my frequency over the total, turn it into a percent, and do that for each line. 4 over 25, 16%, 5 over 25, 20%, and so on. Okay, so I think that's pretty straightforward. Now, what if I have an example like this? Let's say I have grade data for an exam. So looking at this data, and maybe I even know this based on how the exam is structured, it looks like everything comes in increments of a half a point. So it doesn't look like you can get, a quarter of a point or a tenth of a point, but it looks like you can get either a whole point or a half a point as your result. Now, I suppose maybe I could treat this like a categorical distribution. I could say, okay, what are my possible classes? 0, 0.5, 1, 1.5, and so on down to 99.5 and 100. There's going to be 201 of these different classes. And what am I going to have? I'm going to have like a whole bunch of zeros and then a 1, and then a whole bunch more zeros and then a 1, and more zeros and then a... That just made things worse, right? But I do notice that there are two new interesting ideas with this type of a data set. Number one, it does have a natural ordering. So if I do write down my classes, I kind of want to make sure to respect that ordering. I wouldn't want to write like 1.5, 0, 97, 63. I want to respect that natural ordering when I write my list of classes. There's a natural ordering here because if I have a higher measurement, if somebody got a grade on an exam that was higher than somebody else's grade, they like fundamentally did better on that exam. So there's a natural ordering ranking. I want to respect that in the way that I list my classes, number one. And number two, practically speaking, if I listed 201 different classes, that's worse. That's harder to understand. These 201 different classes with a bunch of zeros and the occasional one. That's harder for me to understand than just looking at the raw data, which is already not easy to understand. I don't want to go about it this way. But what I can do, because I have enough structure, I have ordering. With ordering, I know what comes above what. So I kind of have an idea of what numbers are close together and which ones are far apart. So I have ordering. I have the idea in some sense of closeness. If they're ordered, consecutively, they're pretty close. If they're ordered and they have a whole bunch of other instances in between them, they're kind of far apart. Well, maybe what I want to do is I want fewer classes. I can group a bunch of them together. Maybe I can do something like this. I can say, my A's, my A grades are represented by, say, 89.5 to 100. And here I'm thinking of this as a closed interval. So just to be precise about that, I'll put little closed interval brackets on it. These are my, say, A grades. And what I do is I count up uh, all of the data points that have a value between 89.5 and 100. So 88.5, that doesn't make the cut. Neither does 78, but say 95 down here, that does. 100 does, and so on. So as I go through, I find that there are 9 A's. There are 9 data points that fall into this first class. Again, to make this type of group frequency distribution, I need at least ordering. So I need at least ordinal numbers or ordinal data, I should say, so that I know kind of what's close and what's far apart. I can't group Pepsi, ginger ale, Sprite, Dr. Pepper, root beer. Like, which ones should be grouped together? There's, not any really rhyme or reason to that. But these I can group. How should I group them? How many classes should I make? Well, that's a bit of an interpretation thing. It's a question of what are you trying to communicate to your audience? But, typically if you shoot for somewhere between 4 and 10 classes, that's probably a pretty good number. It's probably going to crunch the data down enough that somebody can look at it and get a better understanding of the data from this frequency distribution, or that this is going to lead into a graph that looks pretty reasonable. It's not so many classes that, we either get a graph that just looks crazy, or we get, something like this that's harder to understand in the original data. And it's not so few classes. I mean, if I just group this into like 0 to 50 and 51 to 100, I'm just going to have like, whatever, maybe like 1 and 24, like for my frequencies. That's probably 2 coarse. I don't get any real information from that. But maybe somewhere between something like 4 and 10 classes, that's probably a good medium in most cases, a good happy medium. The other thing about our classes, our bins, so to speak, is our bin sizes should be roughly the same. I don't want to have one of them that's like width 5 and the next one is width 15 and the next one is width 10, because then I'm kind of comparing apples to oranges, right? My bins are different sizes. So I don't really know, like, having a higher or lower frequency. Is it just because my bin was bigger, or is it because there's like more people that are like this uh than, than are like this um that other bin? Now, there is one exception to that bin size, and that's what we sometimes call a catch-all bin. So we can we can kind of look at the data and we can see, okay, like, just at a quick glance, it doesn't look like there's anybody really below 50%. There's a couple in the 50s, 51 and a half, 56, 54, 55 and a half, but it doesn't look like there's anybody below 50. But I mean, the grade data for an exam could go from 0 to 100. Well, I don't see much value in doing, 40 to 50, 0, 30 to 40, 0, 20 to 30, 0, right? That doesn't make a whole lot of sense. So what we'll often do is make a catch-all bin in cases like this, and just say, okay, group all of in this case, all of the Fs together, or all of the folks who are below 59 and a half, just group them all together in one big bin. And if we had a similar kind of thing on top, like if we were measuring people's heights, I mean, a person whose height I measure could be like 3 feet tall, or they could be like 7.5 feet tall. So I might have some bins like, 5'1" to 5'3", 5'3" to 5'5", and so on. And once I get up to like 6'6" or something, or 6'7", I'm like, okay, there's going to be very few people that tall. I'll just make a, bigger than 6'5" or taller than 6'5" category, and maybe a shorter than, 4'9" category or something. And those will just be kind of catch-all bins for the ends. So those are grouped frequency distributions. again, the two important ideas here are, number one, we got to have enough structure to the data to do this. So we have to at least have ordering so that we kind of know what's close together and what's far apart. It probably would be better to have interval data too, so that the differences, so to speak, the bin sizes make sense. But we might be able to get away without interval. Again, it's a question of how is the person that you're presenting this to likely to interpret it? What are you trying to communicate, and how effectively does this communicate that? So we want to have at least ordinal. Interval would probably be preferable. And we're looking at situations where the number of possible outcomes is, say, much larger than 10. We probably want to group in that kind of a situation. Now, switching gears a little bit, we can look at a cumulative frequency distribution. So before, an important component of these previous distributions was that each data point falls into exactly one bin. This first data point on the top left, the D, it goes into the D bin, and it gets counted. That frequency gets incremented by 1 whenever that first data point falls into that D bin. It goes from 0 to 1. And then when I encounter the A bin goes from 0 to 1. The E goes from 0 to 1. The D goes from 1 to 2, 2 to 3, as I'm working my way across the top row. Each data point is counted exactly one time in exactly one bin. Same here. Even though we've grouped them together, we've done it carefully so there's no overlap and there's no potential data point that's missed. 89.5 to 100, 79.5 to 89. So if it's 89, it goes into the second bin. If it's 89.5, it goes into the first bin. Each data point is counted exactly one time in exactly one of these bins. So a cumulative, wanted to scroll over here. So a cumulative frequency distribution, instead of us kind of taking the real line or the part of the real line that we're interested in and breaking it up into bins like this, we're taking the real line. We have some, say, interval of interest. We make a bin. And then what we do is the next line down expands that bin to a larger bin. So this second bin captures all of the data points that were in the previous bin, plus potentially some more. And then we expand the bin further. This next one captures all of the ones in the first bin, all of the ones in the second bin, and potentially some more. We do that again. We expand the bin again. We capture all the ones we had previously, plus potentially some more. And then we do that, in this case, one final time. And now we should have all of the data points. Once we get to the end and we've expanded our bin to where it covers the whole possible range of values for the data that we could be getting, say 0 to 100 in the case of grades for an exam, then we should have captured all of the data points. Our cumulative frequency should be the whole sample size. So if we look at, for instance, the class less than 60, I see that there were 5 folks who scored less than 60, so that is 5. When I go to less than 70 on my cumulative frequency distribution, the second line down, that includes all of the folks less than 60 and the folks who scored between 60 and 70. That is 5 plus 0. Well, that's still 5. When I expand further, less than 80, that includes all of the folks less than 70 plus some more. I see that's those 5 plus 0 plus 6 more, or that's 11 total. Less than 90, again, I expand the bin even further. I have my original 11 that are still in this even bigger bin, plus some more, whoops, plus these 5 more that are in the B category, the B grade category. And then once I expand to 0 to 100, my cumulative frequency is 25. I'm covering the entire range of possible values. So my cumulative frequency should just be the sample size, and it is. So that's maybe a good check that as you're going along, that things have gone according to plan. Any questions so far? I did just realize I don't have the chat up. Okay. So now we can look at this idea of ungrouped frequency distributions. If we have a small data range, if we have a small number of possible uh, data values, we can basically treat the result like a categorical frequency distribution. So here's an example. Provide a satisfaction rating for whatever service from 1 to 5 stars. I mean, it's numerical. It has a natural ordering. 5 stars is a higher level of satisfaction than 1 star. So it has ordering. It might even have the interval nature. But why would I group this, right? There are only 5 possibilities, 1, 2, 3, 4, 5. Am I going to group like 1 and 2 together and 3 and 4 together and then 5 by itself? Probably not. So if I had response data like this, if this was my raw data, these 4 by 4 grid, these 16 numbers, I'm probably just going to basically treat it like categorical data. Now, since it does have a natural ordering, I do want to respect the ordering. So I want to make my classes like 1, 2, 3, 4, 5, or perhaps 5, 4, 3, 2, 1, but I don't want to do like 3, 4, 1, 5, 2. So I do make my classes, my responses, 1, 2, 3, 4, 5 go in order, but I just give each of them their own bin. There was 1 individual that gave us a rating of 1, 3 that gave us a rating of 2, 2 that gave us a 3, and so on. And just like before, just like the categorical frequency distribution, once I get all my frequencies, they should add to the total sample size, and that does happen. And I could represent these as percents if that's more convenient for me. 1 out of 16 is 6.25%, 3 out of 16 is 18.75%, and so on. And these percents add to 100%. Are there any questions so far? Okay, just give me 1 second. Okay, so moving on to the next bit of the slideshow and really kind of the main thrust of this chapter, graphical representations of data. So at this point, we're kind of imagining that we have our raw data that's been collected somehow with some experiment, some survey, whatever. We have a list of raw data, and we've massaged that raw data to get it into some kind of a tabular form, some kind of a frequency distribution. Now I want to take that tabular form and convert it into a graph of some sort. And the first one, the one that we've, I'm sure, all seen before and probably even know how to create, is the histogram. Sometimes it's called a histogram, sometimes a bar chart, sometimes a column chart. But the idea is to use a bar graph to visually represent the frequencies of the classes. So instead of presenting the data like this, 9, 5, 6, 0, and 5 for my different grades, I can represent it like this. Going from right to left, I have 9, 5, 6, 0, and 5. Those are the heights of these bars. The widths of the bars are consistent. So the areas of the bars are proportional to their heights. So when I look at an image, I typically think of like something related to size as being like a two-dimensional thing. So it's more related to area. So by keeping the bars the same width and just changing their heights, the area of the bar is proportional to its height. So that's kind of in line with how people are likely to interpret such a graph. So the histogram, probably the most used graphing technique, uh, and I think for good reason. It's easy to interpret. It's really straightforward, and it's easy to make too, right? I just lay out my classes across the horizontal axis. I lay out my potential frequencies along the vertical axis, and then I just draw bars that have the appropriate height and that are about the same width. Now they can touch or they can not touch. Doesn't much matter. This is the number of stars that we got for our survey response. So this is our 1, 3, 2, 6, 4. We see that we got 1 star, 3 2 stars, 2 3 stars, 6 and 4, 4 and 5 star reviews. Oh, and I think some people might quibble about like if the bars touch it's a histogram, and if they don't touch, it's a column chart. But for all intents and purposes, bar chart, column chart, histogram essentially mean the same thing. If you go into Excel, there are a ton of different settings you can use. You can like outline things, you can change the colors, you can do all kinds of different manipulations to this basic histogram in Excel, or really to any of the charts we're going to talk about. And we'll introduce Excel a little bit later, but just know that there's a practically infinite number of different ways that you can tweak the little details of this picture, but it's still basically going to be a histogram. Here's kind of a computer science joke. The trustworthiness of information by file extension. You see tech is at the top. So LaTeX is kind of a mathematical typesetting software. So if somebody has gone through the trouble of writing something in LaTeX, it's probably going to be correct. PDF, CSV, and so on. And then down at the bottom, you have GIFs, which, um, are so those little like moving picture kind of deals. Like, so if it's a GIF, maybe you shouldn't trust it. If it's a tech file, then maybe you can trust it if you can get the tech file to display in your computer. So sometimes tech files are a little annoying to get them to work nicely. Here's an example of a nice graphical technique that combines a couple different ideas. I'm going to make this a little bit bigger so you can see it a little better. So this was from a few years back. And what it shows is for each state, it has this kind of histogram looking thing, this kind of bar chart looking setup. And you see that on the top right here, we have a legend, kind of tells us a little bit about what's going on. Annual percentage change in population, the more red we are, the higher the growth, and the more dark blue we are, the greater the decline. So light blue declined a little bit, dark blue declined a lot, yellow grew a little bit, dark red grew a lot. And actually just looking at this, just kind of glancing over it, I can actually glean a lot of data, a lot of understanding in a very short period of time because of this combination of these bar charts along with this color coding. So if we keep in mind this is 50 states plus DC, and each of them has 10 bars, each of them has 10 years represented, that's what, 510 data points that I'm looking at right here. Does anybody see anything that kind of stands out to you? I think there's a couple of different things to stand out. Anything kind of interesting? Well, I think maybe one point of interest is like the kind of Southwest over here has had really high sustained amount of growth over many years. And we see that in things like, Phoenix is, notoriously a really expensive housing market. We see a kind of a similar thing with Texas. One thing that really stands out is this huge blue kind of downward spike in Louisiana. Well, that was Hurricane Katrina. So when it really clobbered New Orleans, basically everybody moved out because the whole city was destroyed. You see in that same year, Texas had a little bit of a bump. Looks like Georgia had a little bit of a bump. Florida maybe a little more of a bump than usual. So people maybe moved out to maybe some other places in Louisiana, but also some neighboring states until things were rebuilt. And then we see the population grow again for the next few years after that as people started to return. But again, we can look really quickly across here. We see that, PA, if we're particularly interested in our state, okay, like just kind of a slow and steady population growth for each of the 10 years. So we can drill down if we want to, but we can also just kind of look over the whole map and see if anything catches our eye. I mean, I think it's kind of interesting that like DC and North Carolina and South Carolina both had kind of, or have all had kind of like peaks in growth. I think that might be an interesting thing to think about. Like DC went from slight losses of population to pretty strong growth. Looks like Rhode Island and Michigan have kind of, well, at the time had been losing population for, 4 or 5 years or so. Is there a particular reason for that or not? I don't know, but this is what we would call exploratory data analysis, where we just kind of get a graph of the data, a graphical representation, and we kind of look around and see if there are interesting things. And then I might want to dig deeper. I might want to, look at these years in Rhode Island and see if I can figure out, what was the actual cause of this slight decline in population over these several years. Or maybe, maybe I look in the Southwest over here and ask, what was the cause? What is the cause of these really high population growths over so many years? Uh, or maybe I'm interested in saying, okay, do we have the infrastructure to handle this much growth if it continues? And here's just kind of a slightly more zoomed in version in case you were having trouble seeing it if you're on a small screen. This is more kind of along the science side, so I'll kind of skim over this, but this is the output of a GCMS, gas chromatography mass spectrometry analyzer. Big chemical analyzer. You put a chemical into it, it breaks it apart in certain ways, scans it, and based on where these peaks are at uh, different mass to charge ratios, based on the kind of frequency or the intensity of signal at different in different classes and different mass to charge ratios, it uses that kind of chemical signature, looks at a dictionary of lots of known chemical signatures, matches it up, and says, okay, it looks like this thing here. I think that might be a carboxyl group. I'm not sure about that. So a COOH. So if I'm remembering my chemistry right. Or something similar here. In this case, this is looking at the retention time, kind of the time that it took these different chemicals to make it through the capillary tube. Okay, so what are some other options we have? What are some other graphical techniques we have? Well, we could draw what like everybody in the world calls a line chart. For some reason, some books call it a frequency polygon, but it's basically just a line chart, a line graph. So instead of having columns, instead of having a histogram with above 0 to 59, a bar of height 5, and above 59.5 to 69, a bar of height 0, just no bar, and above 69.5 to 79, a bar of height 6. Instead of that, we just have a dot at height 5, a dot at height 0, a dot at height 6, and then we connect the dots. So when are line charts kind of good to use? And this is a subjective thing. This is kind of an opinion thing. When is a line chart better than a column chart? I would say probably whenever kind of consecutive data points or frequency numbers are somehow like inherently related to one another. So like the people who got D's versus the people who got C's probably are not like inherently related to one another. But if I was looking at a time series, if I was looking at, say, a stock movement, on Monday, Tuesday, Wednesday, Thursday, Friday, going along, well, if I know what the value of a stock is on Monday, if it's $30 a share, it's probably not going to be $1 a share on Tuesday. It's probably not going to be $60 a share on Tuesday. Probably going to be pretty close to $30 a share on Tuesday. That's where I think a line chart is much better. Now I've illustrated it here because we don't have an example like that from our previous data. But we could look at something like this. This is the output of a Sanger sequencer getting sequencing the genetic material of some gene or some part of the genome. And we see this kind of line graph here for each of the different colors. There's a different line graph. So we have like a blue that we could follow, kind of goes up and down. And the blue is the amount of signal related to cytosine, the C base in the DNA. The red is related to thymine, the T base, and so on. So when we see a spike in blue and the other ones don't spike, we can call that cytosine. We can say that that base is a C. And it's a zoomed in version if you were having trouble seeing it. We also have a cumulative frequency graph. This is just a line graph for a cumulative frequency distribution. Again, like I think everybody just calls it a cumulative frequency chart or cumulative frequency graph, something like that. But some people apparently call it an ogive, a term that I had never heard before I started teaching this course, 10 years ago or so. But ogive, or more commonly just cumulative frequency chart. This just takes that cumulative frequency distribution, that table, and does the line chart thing with it, right? If you remember, we had 5 folks who got basically F or below. We had 5 plus 0, still 5 folks who got D or below. We had 5 plus 0 plus 6, 11 folks who got C or below, and so on. So this should be a non-decreasing graph, or roughly speaking, an increasing graph. It should go up, going from bottom left to top right. It shouldn't go like up and then down, because remember, we keep expanding the bin, so we always have what we had previously plus potentially some more. So we should only be, as we expand the bin, we should only be getting more data potentially. Relative frequency graphs. Remember, we can represent a frequency distribution either in terms of the actual frequency, or we can think about that in terms of the percent. The 7 responses who favored A, or drink A, which I forget what it is now, that represents 7/25ths of the data set, or 28%. My charts are going to look exactly the same. The difference is going to be that my y-axis, instead of being frequencies, is going to be percents. So that really is the only difference. But constructing it, drawing the bars and all of that, the visual of the graph is going to be the same. It's just that y-axis that's going to look different. And we already discussed a little bit of the advantage and disadvantages of relative frequencies. Big advantage, we can compare different data sets, different size data sets on the same scale. And if I have a data set that's like size 100,000, it's kind of hard for my brain to make sense of like class A has like 27,500 people in it, class B has 8,400 people in it. I'm not used to dealing with numbers that large. I'm used to dealing with numbers like 0 to 100. I deal with those all the time. So it might be a little more intuitive to represent things on a percent scale because it scales it to 0 to 100. Disadvantages? Well, if I look at this, I know exactly what size data set I have. I can maybe infer from that whether I think it could be a representative sample. If I'm talking about a population of, 300 million people and I have a sample of size 25, that's probably not a representative sample. And then sometimes we actually care about scale. So, all right, any questions so far? All right, so the last thing we'll do today is we'll talk about distribution shapes. We have two slides representing kind of some different aspects of different distribution shapes. We'll probably finish this slide and probably do the next slide when we come back. So the first distribution shape is the bell shape, the bell curve. And what characterizes this is it's symmetric. It has a peak in the middle and it tails off to the sides. So if I think of kind of a perfect bell curve, it looks something like this. It's symmetric. What I mean by that is if I can draw a straight line, I would draw a straight line down the middle going through its peak. And if I flip the whole graph about that line, if I pick it up, flip it over, and lay it back down, it looks exactly the same. That's what I mean by symmetric. It has a peak in the middle, and it tails off to both sides. As I go away from that peak in the horizontal axis, the frequency goes down quite rapidly. A lot of times we draw these curves, these distribution shapes, as kind of continuous functions like this, but in reality, this would be something more like a histogram. So what might this look like if I actually had a data set that came from a bell-shaped population? I'm not going to see a perfect bell shape in any real data set. I can cheat that right side over there. It actually is important. Let me make sure that I get that in the picture. Uh, Let me actually make this one a little shorter, just to make it clear that we are actually tailing off. We do have the peak in the middle, and it is kind of roughly symmetric. Again, with any kind of real world data, we're not going to get a super nice, perfect bell curve unless it really comes from a bell-shaped population and we take a huge sample, 10,000 or something like that. It's not going to look like this. It's going to have some little deviations from what we might expect. But overall, I think this picture falls within this characterization that it's roughly symmetric about a peak and that it tails off to the two sides. If we compare that to, say, a bimodal distribution, that's a distribution with, say, two distinct peaks. So I have two distinct peaks. We call that a bimodal distribution. The mode we'll see in chapter 3 is the most frequently occurring data value. Being bimodal means we have two areas of very high frequency. Bi, like bicycle, meaning two. And then uniform and distribution that's straight across or flat. What might a bimodal distribution look like from actual data? Again, we would have kind of two peaks. They might not be exactly the same height. So maybe something like this where we have a peak here and a peak there. And what might uniform look like? Right, again, it's not going to be perfect. Even if we use something that we kind of think of as like perfectly uniform, like say rolling a six-sided die. If you roll a six-sided die 100 times, you're not going to get exactly the same number of 1, 2, 3, 4, 5, 6. Aside from that being mathematically impossible, uh, 6 doesn't divide into 100 evenly. There's just going to be some sampling error there. There's going to be just some random chance you might get a couple extra ones and a couple fewer sixes on this set of rolls. But we see that it's not really tailing off anywhere. It's not really peaking anywhere. It's kind of more or less just straight across and jittering up and down a little bit, just based maybe on some sampling error. So what are some examples of things that we might see, say, in the real world that result in each of these types of situations? Well, for uniform, often we're thinking of things were manufactured by us to be uniform distributions, like a die roll. When, die manufacturers have gone to great lengths to make dice that come up 1, 2, 3, 4, 5, 6 roughly equally likely, or maybe like a coin flip. There are some more naturally occurring things like, say, birth sex, more or less 50-50. So about equally likely that if you have a kid, boy versus girl. But uniform distributions, when I think of them, my first thought is, okay, this is probably something that was kind of carefully constructed to be this way. Something like a die roll, a coin flip, like the number that comes up on a roulette wheel, something like that. Which bingo ball is chosen, those kind of things. This bell-shaped curve, sometimes also called the normal curve or the normal distribution, or sometimes called the Gaussian curve, named after Carl Friedrich Gauss, mathematician from a couple hundred years ago. This actually comes up a whole lot, all over the place. So things like if you look at height or weight, something like that. If you look at things like IQ, comes up all over the place in things that are measured in nature and so on. And this is actually the result of something, a really interesting underlying phenomenon. We'll see this in chapter 6. There's something called the central limit theorem. And basically what the central limit theorem says is that if you average together lots of small influences on a variable, the resulting measurement of that variable will look like a bell curve. So you think of something like height, there might be a dozen or a couple dozen genetic influences, each of which has maybe a small impact on someone's overall height. There might be a ton of, say, um, I can't think of the word, but of environmental influences, what you eat, how much you sleep, how much you exercise, whatever as a kid that might impact height, but each of those probably to a small level. And they all kind of average together to give you your height. So if you have lots of, let's say, tall genes and not too many short genes, and you have lots of tall environmental influences and not too many short ones, then maybe you turn out to be on average taller. But most people are going to like have kind of some smattering of some tall influences, some short influences, and they're going to end up kind of in the middle. So most people are going to end up in the middle. It's really just the outliers who got, say, lots of switches, tall switches like turned on, or the outliers who got lots of the tall switches turned off, who kind of fall to the ends here. And if that's, say, roughly a random process, it's much more likely to get, say, 5 heads and 5 tails on 10 coin flips than to get 10 heads. I think that's just intuitive. To get 10 heads on 10 coin flips Seems like it's not likely to happen very much at all. Now, there is one thing I glossed over, say for height, for instance. There are lots of small factors, lots of small contributing factors, but there's actually one large contributing factor, male versus female. Males are kind of systematically taller than females. It's just the way the biology works out. So maybe like this would be male height. So if we stratified, if we split the males from the females and just looked at the heights of the males, we might see a nice normal distribution. If we just looked at the heights of the females, we might also see a nice normal distribution. If we combine them together, so height overall, males and females mixed together in the same sample, then we might see something more like a bimodal distribution. Maybe between maybe 5'4" and 5'5" or so is the female peak, and maybe somewhere in the ballpark of 5'9" or 5'10" is the male peak. And what's really happening here is we have kind of the female normal distribution. And we have the male normal distribution. And they're being added together. So the males look like this distribution, the females look like that distribution. And then we kind of add them all together. We're just adding the two heights of these two functions, and we might get something that looks bimodal like this. So when I see a bimodal distribution, my tendency is to think, okay, maybe I have two groups that are fundamentally distinguished by, say, one variable. And depending on the context and what I'm investigating, I might want to stratify. I might want to break those two groups apart, study them each individually. That might give me more information that's more along the lines of what I'm looking for. Maybe not. It depends on what the question is, but that's kind of my initial thought is, oh, it looks like I have two populations that are kind of this one's self-similar, but they're combined together in the same data set. Okay, so that is where we'll leave it today. Let me stop the recording.